start off where we finished from last week, and then I'm going to go back on a couple of the basics of that as well. So just let me have a look. So last week we kind of got as far as the recovery. Then we did the recharge. And I know Shane has fixed some of the bugs on that, so we can practice that. Then the next thing that we were supposed to do after we've done the recharge was we were supposed to go save and exit, go into the workshop area and click on the test skills areas to complete the fault finding tasks randomly presented. So before I do that, so that's section 10, this is before we start on that, what I want to do is I just want to kind of give you a quick reminder and give everyone a kind of a quick reminder before we continue on into section 10 of the troubleshooting. What I want to do is just to remind everybody, okay, we have a standard, so what I'm showing you here in front of you is what you see is a standard vapor compression system, and in this particular case what we're looking at is we're looking at our training rig, okay? Now all vapor compression systems, regardless of what they're doing, what their purpose are, when I say all, 95% of the systems that we are likely to work on or we are likely to come across will be built on the basis of a vapor compression system. And a vapor compression system requires four main components in order for it to operate. In other words, in order for it to remove heat from one area and reject that heat into another area. So the four components that we're dealing with are first and foremost the compressor, which is located here. This is a hermetically sealed compressor. And compressors come in many shapes and forms. So you have hermetically sealed and you have semi-hermetic compressors. The difference being a hermetically sealed compressor is a compressor such as this one, which is completely sealed. You cannot dismantle it. You cannot take it apart. You cannot do anything with it. So once it burns out, or once it seizes, or once any kind of mechanical malfunction happens, you simply replace it, because it is not possible to strip it and take it apart. A semi-hermetic compressor, on the other hand, is like a car engine. You can lift the head, you can take it pretty much apart, you can take out all of the components out of it, such as the crankshaft, such as the pistons, such as the O-rings, such as the valve plate, and you can replace them all, new gaskets, all of that kind of stuff, and rebuild it and put it all back together. Okay, you can also change the oil in a semi-hermetic compressor, which you can't on the hermetically sealed compressor. And then you have everything from a piston type compressor to a scroll type compressor to a centrifugal type compressor to a screw type compressor.
Hello?
Yes?
Yeah, what happens if this compressor is a bit noisy?
What do you mean?
You know, that some compressor is a bit noisy, like, rattling away.
Yeah. So some of these semi-hermetics,
From the compressor.
yeah, some of these hermetically sealed compressors, if they are rattly, there's not a lot you can do about it. You know, some people, I've seen some people, maybe a bit of trial and error where they will add a little bit of oil, but there's no way of knowing how much oil is in the this type of compressor. I've seen other people maybe give it a smack of a rubber mallet when it starts to get noisy. But usually if it's starting to get noisy, it's usually an indication that the compressor's on its way out. And it could be a problem even with your pipe work, that you're not getting enough oil back to the compressor. So you need to consider the job. It's hard for me to turn around and say, because what your definition of rattly is different to my definition of rattly. So unless we're both standing there listening to it, I can't really tell you, what a rattly compressor is. But as I say, usually it's an indication that the compressor's on its way out. Sometimes you'll find that they just rattle on startup and they smooth down after a while. Sometimes you might need to look at the mounting. So again, there are usually on the base of these types of compressors, there are rubber mounts that they're sitting on, and that's to allow for the reciprocating motion as well. So you may need to look at that and make sure that the rubbers that they're mounted on are all evenly the same height. Sometimes you might find there's a rubber missing, and that could be causing your rattling. Other times you might find that one of the rubbers has started to deteriorate and the compressor is slightly lopsided. That could be causing the rattling as well. I mean, if you were just to take that compressor when it's standing still and give it a shake with your hand, it will rattle, and it's basically the way the actual electrical motor is mounted inside in the engine, so it's or inside in the body, so it's the electrical motor in its casing that's actually rattling against the side walls. So, you know, again, it's only by looking at the specific installation that I could tell you why it's rattling and how to resolve it. But it's not good for these compressors to be on their side or to be lopsided, because that will cause problems with oil circulation and cause the compressor to seize over time. So, regardless of what type of compressor, their function, getting back to what a vapor compression system is, their function, regardless of the design or the type of compressor, is to pump refrigerant around the system. So it takes refrigerant from low pressure, low temperature coming back here from the evaporator. So it sucks the refrigerant that's in the evaporator and it sucks it into the compressor, and then it pushes it from the compressor. So basically by the process of compression, it will convert the low pressure, low temperature vapor to high pressure, high temperature vapor and discharge it into the condensing unit. The purpose of the condensing unit is to desuperheat that vapor. Then it condenses the vapor, and then it subcools the vapor before it exits the condenser and heads along the liquid line through the liquid receiver. Now, not all jobs have liquid receivers, but the liquid receiver is not a main component, it is a main accessory. So when I talk about components, there are only 4 main components that I'm concerned about with a vapor compression system, and everything else that you see is an accessory which has been fitted to engineer the system to make it more efficient or to make it serviceable. So we have the high pressure, high temperature subcooled liquid traveling along the liquid line, and it travels as far as the second component, or the third component, should I say, that we talk about. So we have compressor, condenser, metering device. Now the metering device can be in the form of a thermostatic expansion valve, such as this here. It can be in the form of a capillary tube. It can be float valves. There can be hand expansion valves and so on. There are various different types of metering devices, and that's why we refer to them simply as metering devices. However, the most common ones on a commercial system, a commercial refrigeration system, is the thermostatic expansion valve, or alternatively, more and more these days, it can be an electronic expansion valve. This valve then creates a pressure drop, so it actually converts the high pressure, high temperature subcooled liquid to low pressure, low temperature liquid. That liquid then enters into the evaporator, which is your 4th main component. So your evaporator then is the 4th component, and effectively then what happens is that liquid is converted from a low pressure, low temperature liquid to a low pressure, low temperature vapor, and then it is superheated. In other words, it is the sensible temperature of the refrigerant is heated to a temperature above that of its saturation temperature. And basically that low pressure, low temperature superheated vapor is then drawn by the compressor back through the suction pipe back into the compressor, and the process starts again. Now, what I keep saying to you is that we have to concern ourselves about high pressure, high temperature vapor and high pressure, high temperature liquid. And then I talk about subcooled liquid and I talk about superheat vapor. So what we need to remember is that refrigerant gases work on the principle of pressure-temperature relationship. So they have a pressure-temperature relationship. So when we look at our service manifold, okay, this is our service manifold, and we can see on the low side we go up to a pressure of 17 bar here, and if we look over on the high side we can see that we go up to a pressure of 34 bar. So that's how you first of all differentiate the two gauges. The low side gauge is going to have an actual lower limit, and you can actually see the real limit of this gauge is 8 bar. 17 is what it's capable of taking. It's the pressure it's capable of taking, but from our point of view, to be able to use it to get the pressure temperature relationship, to get a reading, the pressure temperature relationship reading, 8 bar is the max that we would be expecting on the low side of a system when we're using it. And again, on the high side, you can see it goes up to 34 bar here, but again, you can see here it's about 33 bars really where it's useful to our point of view, with the built-in extra. 34 bar is a built-in extra. So there, and also then you'll notice as well that the blue representing the low side, the blue color versus the red color. So that's kind of an American idea whereby we would use red gauge manifolds to represent high temperature, high pressure, and we use blue gauge manifolds to represent low temperature, low pressure. And then you'll notice then with the lines, you can see that it's a blue line coming from your low side of the system and your low side gauge. Therefore, it's representing low pressure, and we can see the red line coming from our high side gauge, and therefore we can see that it's representing high pressure, high temperature. Now, the key or the story that I'm trying to build up here is the fact is that if you know the temperature, then you can work out the pressure, or if you know the pressure, then you can work out the temperature. So what I'm trying to get across here is before we go into the random fault finding, is I'm trying to get across the idea that if we had a really good thermometer, we wouldn't really need to put gauge manifolds onto a refrigeration system until we need to actually do something to resolve a problem. So in other words, by using a good thermometer and using some rules of thumb that I'm going to give you, we will be able to determine if a system is operating correctly. And then if we determine that the system has a problem, there is a fault with the system, it's only then that we will put the gauges on to confirm our diagnosis and to carry out a repair. But what I'm trying to do, because of F-gas regulation, because of our conscious awareness of the global warming and ozone depletion, what we're trying to do is we're trying to encourage a practice whereby putting the gauges onto a system is a last resort, as opposed to it being a first resort. So when you're called to a job and you're asked to diagnose the problem because the customer tells you that the system is not reaching temperature, and it can be an air conditioning system for comfort cooling, or it can be a refrigeration system for chill, for ambient warm or high ambient temperature, or a freezer for low ambient temperature. It really doesn't matter, but if it contains F-gas in it, really what we want to do is we want to prevent putting the gauges on, because that causes us to go through the process of purging. So what we want to do is we want to diagnose the problem in advance of putting on the gauges. So sometimes we might be able to diagnose the problem without actually ever putting a gauge line on the system. So that's the key message. Now, the other key message that I need to get across tonight as well is that how the gauges actually operate. So it's very important that you understand how the gauges operate. Now, there is a YouTube video out there whereby I've taken the back cover off and kind of showed you how a Baudouin tube gauge actually works. And really what I'm trying to do here tonight is I'm trying to just explain to you then the importance of being able to understand when these valves should be open and when they should be closed, so that you don't make the mistake of inadvertently allowing refrigerant to escape the atmosphere, or inadvertently allowing high pressure go across to low pressure when you're trying to diagnose a problem with the system. And also then to help you to understand as well how to remove gauges from an actual system without losing refrigerant off the atmosphere as well. So what we do is we'll start with explaining how they operate. Now, in your notes, in your little collection of notes, there is a book called Refrigeration Equipment Book, and when it's a PDF file. Refrigeration Equipment is the name of the file, and when you go into that, there's a table of contents all the way along, and it gives you various different things: installation, vapor compression system, servicing, and all that. But halfway through it, then it's page 10 here. You can see it's a 234 page book, but page 10 of it, you can see here there's a service gauge. It explains the service gauge manifold. And again, what we're seeing here is we're seeing the low side gauge manifold represented here with number 1, and we're seeing the high side gauge manifold represented here as number 2. We're seeing number 3 is where you would connect your low side hose. This one here with the arrow is where you actually connect your yellow service hose. So your service hose is usually connected to your refrigerant bottle for charging up the actual system, or it can be connected to your vacuum pump for vacuuming out the system. Or it can be connected to your nitrogen gauge for pressure testing an empty system. And then number 4 is representing the service port, whereby the refrigerant from the high side. So your red hose line is connected to the refrigerant from the high side. Okay. And the purpose of this diagram is to try and show you, okay, that what we have is once you put refrigerant, so say our blue hose is connected to the low side connection here, the blue hose is connected to the low side connection here. Once you have the blue hose connected to the low side connection, once there is pressure in that blue hose, it goes straight to the gauge. So this gauge is actually will give you a reading as soon as there's pressure. So say this is representing 0 where the little hand is, and you can see here that's representing maybe 1, 2, 3, 4 bar or whatever. And the same on this one. This will be representing 0, and this is representing a pressure. Now, as soon as we put pressure in our hose line, it goes straight to the gauge. So how I demonstrate that to you is I simply go here, and I'll simply, again, I explained to you about the Schrader, but I'm simply just going to connect the Schrader. So straight away, all I've done was taken this hose and connected this hose to the Schrader fitting on the low side of the system. I disconnected, that'll go back to 0 in the real world. That's a bug for Shane to sort out. And I connect it again, it goes to back up to pressure. So I'm hoping it's not going. So hang on, we'll just go save and exit, excuse me for 1 second, and then we will start again, and then we will skip the login, and then we'll go back in here. I'm just trying to reset it because of that little bug that it didn't go back to 0. And just to show you one more time, okay, we have our gauge at 0. This is dangling in the air, so therefore it's reading 1 bar atmospheric pressure, which is the equivalent to 0 gauge pressure. So again, remember, absolute pressure at sea level is 1.013 something or other bar, 34 bar or something like that. But what we have here is we have a reading of 0. So gauge pressure is always going to be 1 bar less than absolute pressure. But as soon as I connect my hose line on, I get pressure reading straight away. Now I haven't done anything with these valves. So that brings me back to what I was trying to show you a little bit earlier. So
the one digital gauge, that be better one, or gauge that one is be better?
Yeah, again, it's doctors different, patients die. It's whatever you're comfortable with. It's whatever you're used to using. So yes, there are digital gauges out there. There's no point in saying one is better than the other. The analog gauges that we're looking at here, which is the mechanical gauges that we're looking at here, are basically bulletproof to a certain extent, and the digital gauges, they're more expensive, and you have to mind them, and you have to make sure that they're calibrated as well. So you'd have to get a calibration cert to make sure that the digital reading is correct, whereas the mechanical, we can actually calibrate ourselves in our but basically there is our calibration nut here. So there's a little plastic covering. Usually you take that out, you put your screwdriver in, and if I zoom in on it, you will see that I'm able to plus or minus. So this is for 0. So as soon as I have no pressure on the gauge line, I don't know if the bug is gone. No, the bug hasn't gone. As soon as I have no pressure on the gauge line, the first thing I do is I check and make sure. So if I go over to this one, which is at 0, the first thing I do is I check and make sure that this needle is lined up with the 0. And how I do that is I actually adjust this screw minus or plus just to get that lined up here. So that's something I can do myself, and something I do every time before I put the gauges on. If you have a digital, then you're going to have to maybe get it done once a year, calibrated by a professional company, and send it off to get it done to make sure that it's not knocked out of calibration and you are getting correct readings. But it goes back to the other thing that I was saying is really a good digital thermometer. You'd be better off investing in a good digital thermometer, and that'll become more obvious in a few minutes when I go through explaining how to use a thermometer, and you only use gauge manifolds as a last resort. So sticking with just looking at this manifold, really what I was trying to show you is by on our simulator, what I was actually showing you is that as soon as I connected the blue hose on, pressure went straight to my gauge manifold, and it went straight to the to give me pressure on the manifold. Now, the other thing that you will have noticed once I did that is that no gas came out of this yellow line, and that's because I didn't do anything with my shut-off valve. So my manifold shut-off valve, it was closed, or it is closed, okay? And because it is closed, that basically means then, because it is closed, that basically means that the refrigerant went straight to the gauge and didn't actually enter into the manifold chamber, all right? So therefore, no refrigerant escaped out here through this yellow one. Now, if I had made the mistake of opening this actual valve, so this shut-off valve, all right, the low side shut-off valve, if I made the mistake of opening that, refrigerant would have entered into this manifold here and leaked out to the yellow hose line. So one of the other things that you'll notice, this service line, what I've done with this service line is I've actually blanked it off. So rather than leaving it dangling, sitting here down like we have these two red ones here, I actually get the yellow and I blank it. I fit a blank onto it, or I put it onto a blank connection on the actual manifold itself. And the reason for that is that if I want refrigerant to go from my low side, which we have here at the moment, and remember when we go through the purging process, one of the other things that we do is we fit the red line here, okay, and you'll notice that the red line is still, or the red gauge is still registering 0. That's because we're using a different valve here. The service valve that we're using here, okay, is a service valve that requires a valve ratchet to crack it. So basically what the terminology that we talk about is you have the valve in the fully backseat position. So this valve at the moment is in the fully backseat position. Then the valve can be cracked, and once you crack it, that means then that refrigerant can now enter into the red hose line, into the service line here, and we will get our pressure reading here on our gauge. And then you have another piece of terminology which is fully front seated. So if we were to fully front seat the valve all the way, and again I'll show you a valve operation as well in a few minutes, and I've already shown you valve operation, but I'll just remind you. But if we go fully front seated, then basically what you will find happening is that the refrigerant will no longer be able to enter into this hose line, but into this pipe, into this liquid line pipe, but this hose line will still be exposed to refrigerant. So the only time your service port is not exposed to refrigerant is when you have the valve in the fully backseat position, okay? Now, effectively, if I want to go and I want refrigerant to go from this side here into my manifold and into my red hose line, I have to open the valve here, which is not allowing me to do because I'm not in the purge sequence. So maybe I need to go and just do this sequence here just for the sake of it. Okay. So literally we go again, we see pressure going straight through. When I open this one, okay, apologies because I'm not doing the steps it wants me to do because I'm in a fierce hurry altogether. Terrible to be young and enthusiastic. Anyway, so I open this lad here, and you can see once I open this lad here, now refrigerant will enter in here. So what does that mean effectively? That means that as soon as I open this shut-off valve here, the refrigerant that's in this area here that's feeding pressure or giving my gauge pressure, as soon as I open the shut-off valve, the refrigerant enters in here into the service area. So now my yellow hose line is full of refrigerant, but thankfully we have it blanked off. My actual valve manifold has got refrigerant in it as well. So in other words, the refrigerant has now gone from my blue side chamber stroke gauge area into my manifold area and hasn't gone any further for the moment. Now the next thing that I have to do is I have to open this side. So by opening this side, now what's happened is that the refrigerant has, by opening this shut-off valve, the refrigerant has now entered into the high side chamber, and that's why we had 4 bar registered on this side, 4 bar registered on this side on our simulator. Okay, so it's kind of shown down here a little bit more. You can see when the shut-off valves are in the closed position, refrigerant will only go into the respective gauge, into the respective gauges, or will enter through the respective gauge ports. Okay. As soon as I open the high side shut-off valve, any high side refrigerant that's coming from my high side gauge will enter into my service area and exit out of my yellow service gauge. Okay. The other way you can see where we open the low side shut-off valve, so we have the high side closed, we have the low side shut-off valve closed. Again, what will happen is any refrigerant, say in this case, because the arrow is going this way, it's actually saying any refrigerant that's coming from my my bottle, for example, will basically come from the bottle and enter into the blue hose line and into the actual system again. And then this last one is kind of showing that if I have the high and the low, so refrigerant will go between the two. So it will pass from the red side to the blue side. And obviously the arrows are going this way to the left because we're going to have higher pressure. So effectively what happens is the high side will dominate. So in other words, the high side will go across into the low side and equalize across. But you will constantly be getting pressure coming from the high side across into the low side if we have the both manifolds open. But as I was trying to show you also then, because we had in our own simulator here, because we have no gas, we are not exposed to the high side of the system. We have no gas in this hose line because we didn't crack our valve. But we do have gas in this hose line because we fitted it to a Schrader fitting, which acts in the same way as a car tire or a bicycle tire or whatever. And because we were able to open this, we allowed the refrigerant to enter into the manifold. And then when we opened this, we allowed the refrigerant to travel into the high side of the system, into the red hose, and this is where you're getting your equalization taking place. And that's what's allowing us then to go along here and carry out our purge, which is literally just allowing enough vapor to escape out of the red line. And it's a judgment call. We have to remember that it's going to be a very small amount of air in the system. So it's a judgment call. What we're trying to do is we're trying to leave it purging for long enough so that we know that there's no longer air coming and there's only refrigerant coming out. But we want to prevent or minimize the amount of refrigerant that we let out. So we have to remember that it's only a slight purge that's needed because the quantity of air that we would have, which is going to be heavier than the refrigerant, so it's being pushed by the refrigerant. It's going to sit on top of the refrigerant. So, sorry, it's not heavier. It's lighter than the refrigerant, but it's going to sit on top of the refrigerant, and it's being pushed by the refrigerant out the hose line. So as soon as we loosen the hose line, we have to be able to close it when we think that we've finished purging air and we've now just got refrigerant, and it only needs to be a short, sharp purge as opposed to a big long purge. Because again, this is why I'm coming back. I'm going to harper back on about a last resort. We do not want to fit gauges on as a first resort. We want to get into the habit of fitting gauges as a last resort. And if we can get away with diagnosing and fixing the system without fitting any gauges, that's all the better. So we try our best not to fit gauges. Now that we have completed that purge, right, one of the steps it tells you here is to close the low side manifold. And that's very important that we close that manifold. And the reason why is because, and I close the high side manifold, and the reason why is because that when I go and I get my valve ratchet, right, so I go and I get my valve. Now, as you can see, there's 5 bar here, there's 4.5 bar here, there's 4.5 bar, 4.5 bar, realistically. That has stayed the same even though I've closed these two valves. Now, the reason why we need to make sure these two valves are closed or shut off is because as soon as I put my valve ratchet onto this job here, if it allows me to do it.
Yeah, from there now.
Thank you. Okay, so what I did was I fitted the valve ratchet on. What I did was I cracked the valve ratchet by literally just, you can see just a quarter of a turn there. And then once I cracked the valve ratchet, what you see happening here is on the high side of the gauge you see 15 bar. On the low side of the gauge you still see the 4.5 bar that's there, or just over 4 bar, 4.4 bar. Now, if this valve was open, this shut-off valve was open, and this shut-off valve was open, then we would be going back to the scenario that you see in the book is this scenario here. The 15 bar would be coming across into the 4.5 bar. So basically what you would find is there'd be a slight drop on the 15 bar on your gauge manifold and a slight increase on your 4.5 bar, and you would be getting constant high pressure going across into the low pressure, and that would give you the same characteristics as a compressor not pumping properly. So that would give you the same sets of faults that you would expect, or sets of the same relationship as a compressor not pumping. So it's very important that we isolate. So basically by keeping the manifold valves closed, we are isolating the high side from the low side. And it's very important that we must understand that when we go to fit gauges onto a system, we check and make sure that the low side shut-off valve is in the closed position, the high side shut-off valve is in the closed position, the rubber ends, the rubber seals at the end of the hoses are in good condition, that the yellow service area is actually sealed and it's actually fitted to a blank port on the manifold. Usually on the manifold, it can be on the side like this one or on the back of the manifold. And once we've checked all of that, and then we go back to calibrating it and making sure that our gauge lines are sitting at 0 and 0. So again, we check for all that. And once we've satisfied that we've the manifold meets all that criteria, we then go and fit the hoses as we've just done. And the only reason why we're opening these two sides and letting gas go from one side to the other side is because we want to complete an actual purge sequence, and then we close them again. Now once we have completed the purge sequence and we are at this scenario here where you get 4.5 and 15, we have no business opening either of these manifolds while we're just looking and getting temperatures and getting pressures and doing our commissioning checks and all the rest. We've no business opening any of these. The only time we would want to open these two shut-off valves is when we want to either add refrigerant in via the service line, the yellow service line, or when we're actually taking the gauges off at the end and we want to be able to get rid of whatever resulting liquid is inside in the actual yellow line before we take it off, because we do not want to allow liquid to escape to the atmosphere. So we take every commercially viable step to allow to remove any liquid from the hose lines and make sure that anything that escapes is only a small bit of vapor, and we try and make sure that anything escaped is down to inadvertent venting. In other words, we have done everything that's commercially viable to make sure that we haven't deliberately allowed more refrigerant than is necessary to escape off. And in actual fact, the reality is that if we were using our thermometers and only putting the gauges on at the minimum, then we would probably never have a problem with refrigerant leaking off to atmosphere, because it's done by man. Every refrigeration system that exists should never leak. It's not like a car where you have to top it up with petrol or top it up with oil or whatever. Every refrigeration system that's there should never ever leak out of the system. If there's a proper maintenance routine in place and there's proper servicing of the system and there's regular leak checking of the system, there's no business for that system ever to lose its charge, other than human error. That's the only reason why it does it. It's because of human error. Now, backseat the high side service valve, so that effectively is me going here, and it's effectively me backseating the valve like so. That basically means that what I've done is I've put it into this position. I've gone from this position and I've put it into this position. And by putting it into this position, no new refrigerant can now enter into this area here. Okay? So the next thing it says on it, open the high side manifold. So effectively what I'm going to do is I'm opening the manifold here. And by doing that, I am, if we go back to our service gauges here, if we go back to our service gauges, if it allows me, where was page 10 is what I'm looking for. So our service gauges, by me opening, I've effectively then, I wonder, is it good? There is better pictures I think further down. I just want to have a look and see. Sometimes there is better pictures, but it's not there at the moment. Okay, all right, apologies, I just go back up. Okay, so what I've done is, by opening it, I've done this one here where I've allowed the refrigerant to go from my red hose line into my service area here. Okay, so now the high side refrigerant is going to cross into this service area here. So I have refrigerant in my yellow line, and I have refrigerant coming from my red hose into my manifold. So the refrigerant is here. Next thing says it's open the low side manifold and allow the gauges to equalize. So watch. Okay, so effectively what you see here is you see the gauge went down from 15 bar down here to just 4.5 bar, and this one here should be around the same. It should be around 4.5 bar or whatever. Two pressures equalize. So this is saying 3 bar, but in real terms, if this says 3 bar, this will say 3 bar. If this says 4 bar, this says 4 bar. So the pressures will equalize in real terms across. So the high pressure will come down to the low pressure. And effectively what that means is that because I've gone to this situation, which is this situation here, I've opened this shut-off valve, I've opened this shut-off valve. High pressure has come from the red hose across into the service area, into my yellow line, and across into my blue line. Now, the fact as well is that because I had my valve in the back-seated position, so when we go back to my valve here, because I had my valve in the back-seated position, this valve here in the back-seat position, no new refrigerant is coming from the liquid receiver. Therefore, this hose line is only under pressure because of the actual gauges themselves. So the only reason why it's under pressure is because the gauges themselves are allowing the high side, whatever was in the high side hose, access to whatever's in the low side of the system. So basically we're in this scenario here. So basically the pressures have equalized across here and no new refrigerant is coming in because of our back-seated position. So it says turn off the solenoid weight and wait for the gauges to reach 0. Now I haven't closed this and I haven't closed this. I've left these in the open position. And as soon as I knock off my solenoid, okay, basically no more refrigerant is allowed to go past the solenoid valve, and you can see then that what happens is all the refrigerant that's on the low side is being sucked out of the low side, pushed back into the compressor. Compressor pushes it to the high side of the system, and the liquid refrigerant will go as far as the inlet of the solenoid. So it's only going as far as the inlet of the solenoid here, which is this point here, right? So it goes to this point here. Now, because there's no new refrigerant entering into the evaporator, the compressor eventually runs out of refrigerant to pull out of the evaporator, and that's why it's going to a 0 reading. So it gets to a 0 reading. And we have a low side pressure safety switch here, or a pressure switch here. And again, I'm hoping to go through each component as well and explain what each component is. But we have a low side pressure switch here, and that pressure switch is wired to cut the power to the compressor, so to stop the compressor from running. So effectively now the noise that you were hearing in the background, if I turned up my volume again, what you will find is no longer there, because the compressor is no longer running, because it's been switched off or de-energized, or whatever way you want to put it. It's the contact, the 220 volt contact is open via the pressure switch, and therefore the power supply is killed to the compressor. Okay, now before I take off my gauges, I'm going to close my high side manifold, and then I'm going to close my low side manifold. So by having the two shut-off valves closed, I now am able to remove the gauges from my system. So as soon as I go and disconnect my red hose, you'll hear nothing. No gas escaping because it's at 0. And then if I go and remove the gauge from the low side, no gas is escaping because it's at 0, and we've completed the pump down. Okay. So this is what we're trying to install, is that the idea that when we go and fit gauges on, it's a last resort, and because we have to fit gauges on, we must be very conscious of minimizing the amount of refrigerant that actually escapes to atmosphere. There's two reasons. Obviously there's the environmental reasons, which is very important, but there's the economical reasons as well, because the cost of refrigerant is increasing all the time. And in fact, I said there was two, there's probably three, because the third reason is that every time you put on and off the gauges and you're letting a little bit of gas out, you're actually reducing the charge, or over time. Now it might take a long time or a multiple time of gauges, but over time you start to reduce the charge of refrigerant. And if you get to a stage where you reduce the charge of refrigerant to a point whereby the refrigeration system stops working efficiently or starts to give trouble, then you have a scenario whereby you have a system that's slightly undercharged. That requires you to go and carry out a full leak test on the system before you can add refrigerant. So if you ever come across a system that has the operating characteristics of a system that is short of gas or undercharged, then you must make sure first and foremost that that system is leak tight before you can add refrigerant to that system. It is illegal to go and assume that has lost its gas charge because somebody was putting on and off gauges or because of human error. It is a legal requirement for any engineer to carry out a full and comprehensive leak test before they would ever add refrigerant to a system that's running short. So it's important that you are aware of that. You cannot add refrigerant to an operating system that you suspect or that you know has a leak. And an old practice that was out there that doesn't happen anymore because it was made illegal, but an old practice was going back a few years, is that a very small pinhole might appear, and it was very difficult to find that actual leak, and required an actual body of time to be put aside and a full pressure test to be carried out, and a fairly comprehensive leak test to be carried out in order to find it. So what used to happen is the contractor used to say, well, we'll just top it up. We'll just add a little bit more refrigerant into it to keep it going. And in 6 months' time, that pinhole will get bigger. And over time, it'll get bigger to a point that it'll be running short of gas a lot sooner. So instead of running short of gas every 6 months, will start running short of gas every 3 months, or it'll start running short of gas every week, or it might get big enough that it'll start running short of gas the minute we put it in. And then that means we can find it. In other words, the less time it holds its charge, the bigger the leak, therefore the easier it is for us to find it. Now that is a highly illegal practice. The practice you might have heard all established fridge men talking about the process of topping up. It's illegal. Don't do it. Don't. Regardless of what a shopkeeper, they might be used to that. A shopkeeper that's in the business a very long time might have been used to that practice. They might insist that you do it. Don't do it, because you will be prosecuted. They will be prosecuted, and you will be prosecuted. So it is very important that you understand that under the F-gas regulation, a contractor or an operator that knowingly adds refrigerant to a system, or that adds refrigerant to a system that they know has a leak and haven't signed, or even suspect it has a leak and haven't signed off on it, that's against the regulation. That's illegal, and you can be prosecuted for it. So that's important that we're aware of that. Now, now that I've got that kind of rant out of the way, I'll get back to what I was really trying to say. I'm really trying to say is that when we go and carry out this one here, which is the portfolio, and we were asked to do this one, save and exit the workshop and go into the test skills area and complete the fault task randomly presented. What I'm trying to say to you is that the best thing that we can do for this is use a gauge. Now, is use a thermometer. Now, I'm not going into the fault finding area for the moment, because I suspect in the back of my head, and I could be wrong, I hope I am, but I suspect in the back of my head that the fault area, it doesn't give us the same freedom with the thermometer as it does as we have here. Would I be right, Shane? Anyway, so thermometer, okay. If I go and I fit, I can try, yeah. If I go, it does work. It does work. It does work. I like them. I like it. I like your positivity. It does work. Okay, so what that means, number 10 is that we save and exit. You probably saw me doing that. If you didn't, I'll do it again. We're in the workshop area here, which is here. It says save and exit, which is this one here, save and exit. Now, I skipped the login because it's too much. Well, if you just wait for a few minutes, you can see you click to start. And then we skip the login, so we don't bother. And then, but you guys actually maybe shouldn't skip the login, because we want to capture that data. So don't skip the login for yourselves. Actually do the login. So if I go back, sorry, just to say save and exit. You guys, you have to wait a few minutes. Saving player data. Then when we go to click to start, I would actually ask you guys to log in. And the reason why I'm asking you guys to log in is we want to capture that data, because that data will be used as evidence as well for the external examiners when they come on board, when they come in to carry out their audit of us. We will be able to show that data and show that each individual, each unique username, how many hours you were in the simulator, what you did, how many times it took you to get the fault, how you improved over time, how you disimproved over time, whichever way it works. But in our case, how we improve. So I would actually recommend that you log in, okay? I'm skipping it because I'm old and I can't remember my password. So when we go in here, when we actually eventually get into this area, you can see here the number. There's 9 faults that need to be assessed. The number of attempts in my particular case is 0, so I haven't attempted any of those faults. So I'm going to click on number 1, which is the first fault that I want to click on. Now, assuming that what Shane tells me, maybe, yeah, that's it. The thermometer does work, but I can't get into the evaporator, for example. So I need to be able to get into the evaporator and be able to measure evaporating temperature. I can't do that because I can't actually.
Go to the camera there and go to the back.
I can do that. Excellent. Right, now, with my thermometer, the main difference between this setup that we have here and the setup that you have in the previous menu, which was the workshop setup, was that the thermostatic expansion valve on this one is in the correct place. It's at the inlet to the evaporator. It's not out on the bench like we had earlier on. It's at the inlet to the evaporator. So if I put my thermometer at the start of the evaporator, so anywhere just at the outlet of the thermostatic expansion valve and the inlet of the evaporator, so where the bulb is clamped is representing the outlet. So if I was to put my thermometer there, you can see it says the end of the evaporator coil, so that's representing the outlet of the evaporator. So that's your suction pipe going back to the compressor. This is your high pressure, high temperature liquid going into your thermostatic expansion valve, pressure drop created, and here we've got low pressure, low temperature liquid entering into your evaporator. Now, so I know that you're probably saying, well, I'm not going to take the cover off. So I mean, really, in realistic terms, okay, if I was to actually get my probe, my thermometer probe, and stick it through the coil and pick up this pipe here, it's the same. I'm going to get the same temperature. And if I go along and follow that pipe and I come along here and I pick up this pipe here from the front, it's going to be the same temperature. And if I go along and keep going along and get to this pipe here, it's going to be the same temperature. It's only when I get to the likes of this section here, this top section here. So it depends on whether you're bottom or top entry. So it depends. In this particular case, we're bottom entry here. The expansion device is on the bottom entry. And what I would suggest you do is you try a few different places and then you take an educated guess. But what will happen is that at the outlet, so we've got 10 at the inlet. If I take this pipe here, which is the outlet pipe, you see there's 20 degrees, right? So that is telling me that we have superheated vapor in this section of pipe, whereas this section of pipe is telling me that we have saturated vapor, saturated liquid in this section of the pipe, okay? So when we have a liquid and vapor mix, our latent heat will be a saturated latent heat. So in other words, it's going to be constant pressure and temperature going through the evaporator. So when I measure with the thermometer, I will get my constant pressure temperature or my constant 10 degrees temperature in it. As soon as the 100% vapor occurs inside in the actual evaporator, then the thermometer, all the thermometer ever does is measure sensible heat. The thermometer is able to pick up on the sensible heat change. So that's how we can get our superheated vapor temperature. Or I'd rather just say that we get our vapor temperature at the outlet and we get our liquid vapor mix, or liquid vapor mix temperature at the inlet. And the difference between the temperature at the inlet of my evaporator and the temperature at the outlet of my evaporator is my superheat value. So we have to remember that superheat comes as a value. It doesn't come as an actual temperature. We're not worried about it as a temperature, or we don't think of it in terms of a temperature. We think of it in terms of a value. And the reason why we think of it in terms of a value is because what we're trying to do is we're trying to use it as an instrument to determine that the evaporator has a sufficient amount of liquid in it in order for it to achieve its refrigeration effect. So what do I mean by refrigeration effect? In other words, refrigeration effect is the rate in which the evaporator is able to remove the heat from in this case, the cold room, and bring the temperature, the air temperature down, and in turn bring the product temperature down. So therefore, the superheat is really only comes into effect is to be able to allow us to determine that there's sufficient amount of liquid, so the liquid level inside the evaporator. But the other reason for superheat, or the only reason why we have superheat in the evaporator as well, is to make sure that the compressor only has vapor coming back to it. Our refrigeration compressors only pump vapor. They do not pump liquid. So superheat has been built in or engineered in to the process so as it can protect the compressor from liquid slugs getting back. So that's the only reason why superheat takes place inside in the evaporator. Now, on a comfort cooling split air conditioning system, we don't even worry about superheat, because the way they're designed is they have what's known as a suction accumulator, which will separate any potential liquid coming back from the vapor and only allow vapor to go back to the compressor. And often you might find, depending on how much work has to be done, how much heat needs to be removed, and what the temperature is, whether it's pull down temperature or holdover temperature, you may find that on your return line coming from your indoor unit back to your outdoor unit, it will have a slight bit of liquid in it, or there will be a mixture of liquid. So only the proportion of liquid that's needed to boil off to remove the heat boils off. And then you will find that back at the compressor, before the suction pipe enters into the compressor, a suction accumulator is fitted, and that suction accumulator will separate the liquid from the vapor. And again, when you come back to site, there is a slide which shows you a suction accumulator, and I'll explain that to you as well. But when you come back to site here, I will actually show you a physical suction accumulator that I've taken the sides out of, so you can see into it, for an air conditioning, a split air conditioning unit, and for a commercial refrigeration unit. You'll see how they work then as well. But anyway, getting back to what I'm trying to say in terms of finding out what this fault is, right? We need to be able to answer this question. So basically there's a chart here. So if I click on this chart here, right? There's a chart here, and we need to be able to answer this question in terms of the chart, right? So the very first question, I'll just get rid of this guy here for the moment. The very first question is, it says here, is LP too low? So basically what we do is we use this fault finding chart to be able to determine by process of elimination what the problem isn't, so that we can confidently say what the problem is. Okay? So the first question is the LP too low? Is the evaporating pressure, LP stands for back pressure or low pressure. LP is low pressure. You'll hear me talking about back pressure, and you'll hear me talking about evaporating pressure. Those three are the same. So evaporating pressure, low pressure, back pressure, they're the same. So my evaporating pressure, is my evaporating pressure too low? And that's a question. So really the question is it too low? But if you wanted to think of it in other terms, the question is it too low? Is it normal for the ambient condition that the evaporator is placed in? Or is it too high? So it all centers around the ambient condition. So again, going back to pressure-temperature relationship, as pressure increases, temperature increases. As pressure decreases, temperature decreases. Okay, it's not there. Okay, it's not there. I was going to see if we had the slide chart, but we don't. Okay, I was going to see if we had the slide chart there, but we have it in the other one. But anyway, you know the slide chart. You've seen the slide chart. In fact, I don't even need to worry about the slide chart. I can just go back into the room, and here's my slide chart here. If I just click on that, there we go. Look. So this is my slide chart. So this is my pressure temperature slide chart. So we've got pressure here going up along. And we've got temperature for the different refrigerants for 407C, R22, 134A and 404A, okay? So depending on the refrigerant that's in the system, okay, for every temperature there's a corresponding pressure, or for every pressure there's a corresponding temperature. And the one thing that you will notice, even though these temperature ranges are different as for equal pressures, the one thing you will notice is that the higher we go up in pressure, so we're up at 8 bar here, you can see 407C is plus 20. You can see anything above 8 bar. You can see this red one, which is R22, is at plus 20. You can see that up and around 8 bar, or just above 8 or 7.5 bar there, maybe even less, 7.2.3 bar. You've got plus 10 degrees for 404A. You've got here just under 6, just over 6 bar, so going across there, 6.1, 6.2. You've got plus 30 degrees for 134A. I think this is the blue one here, 134A. Okay, so what that means in real terms is the higher the temperature coming onto my evaporator, right, the higher my evaporating temperature is going to be. The lower the temperature coming onto my evaporator, the lower my evaporating pressure is going to be, stroke temperature. Okay? So the question that we are being asked in this chart here is that we have turned around and we've asked ourselves, is the back pressure too low, right? So in order for me to be able to answer that, I need to know, well, what is normal back pressure? How do I know that temperature is normal for the room temperature that we have? So if we look at our room temperature, you can see here is if I show you the thermometer inside in the room, we can go in here and we can see thermometer inside in the room, degrees Celsius. We can see that it's 20 degrees Celsius. But you also can see by me putting my probe to the air on, to the evaporator, which is the air coming from the room temperature back onto the evaporator. So that's the air that contains all the heat that's been removed from the product and from the thing going onto the evaporator. And that then air gives up its heat to the refrigerant, so that's what boils off the liquid refrigerant inside in the evaporator, so that when the air is coming off, you're going to see the air coming off here at a lower temperature than it comes on. So there's a temperature difference of air on and air off, okay? And in order for me to be able to determine that the evaporating temperature that we got from inside in the evaporator is normal, we need to be able to say, okay, it has to be, we have to work out what I refer to is the delta T total. And the delta T total is the difference between air on temperature, which we have here 20 degrees, and evaporating temperature, which is the temperature of the refrigerant, liquid refrigerant vapor mixture inside, or it's the saturation temperature of the refrigerant inside in the evaporator. So in other words, evaporating temperature is the temperature of the refrigerant inside in the evaporator versus the temperature of the air coming onto the evaporator. And for a refrigeration system such as this one, so this is just your standard chilled cold room. So for any commercial refrigeration system, your domestic fridge, your ice bank, your even to your water chillers, well, not water chillers because water can be 10% more efficient. So, but in some cases, your water chillers, I'll come back to you on that one. Your beer coolers, your butcher's cold rooms, your, and so on and so forth. So your refrigeration systems, even your ice cream freezers, and so on. The delta T total should be between 5 and 10 degrees of a difference. Okay, that means that the air on here, if the air on here is 20 degrees, which is in this case is 20 degrees, okay, we would expect the evaporating temperature to be either 5 to 10 degrees lower. So if I take 10 off 20, that's 10 degrees, so therefore that's within the range. But I could go, if I take air on at 20 and I take 5 off, I can go to 15. So normal for an air on temperature of 20 degrees, normal for an air on temperature of 20 degrees, normal evaporating temperature is anywhere between 10 and 15 degrees. So we're able to answer this question, not this one, sorry, this one. We're able to answer this question, no. Is LP too low? We're able to say no because we know that for this particular type of system, the delta T total, the difference between the air on temperature and the evaporating temperature, can be anywhere between 5 to 10 degrees of a difference. In this particular case, we have 10 degrees of a difference. It's the maximum amount of difference we're allowed to have, but it's within the range that the evaporator has been designed to operate. So it's 10 degrees lower than the air on temperature. It can be anywhere as low as high as 5 degrees less and as low as 10 degrees less, or anywhere in between. In this particular scenario, it is 10 degrees lower. That's within the norm. Therefore, we can with confidence say, is LP too low? No, it's normal. It's within the operating range. So the next question we look at then is HP too low? So HP stands for head pressure, condensing pressure, okay? And again, in order for us to be able to answer that question, we need to be able to determine, well, what is normal condensing temperature for the ambient condition that the condenser is located in. So one of the things that you will notice here, the room temperature that the condenser is located in, you can see there it's about 10, 11, about 12 degrees temperature there, degrees Celsius, right? So that's the room temperature. But really, if I go and get my good thermometer and I put it to the face of the condenser, we can see that the air coming onto this condenser is plus 20 degrees. Now what we need to do is we need to determine, well, what is the temperature of the refrigerant inside in the condenser. In other words, again, remember, we have desuperheating zone, and you can see the very top of the condenser is desuperheating zone. You can see the temperature of the refrigerant is 63 degrees Celsius. We have condensing zone, which is the middle of the condenser, and you can see our condensing temperature is 18 degrees Celsius. And we have subcooling zone, so we can see that the temperature of a refrigerant at the bottom of the condenser is 12 degrees Celsius. And we know that the difference between our condensing zone and our subcooling zone, so the difference between the middle of our condenser, the temperature at the middle of our condenser, and the sensible temperature at the bottom of our condenser, the difference between those is our subcooling value. So in other words, again, similar to what happened inside the evaporator, you've got high temperature, high pressure, superheated vapor being desuperheated in the first pass of the condenser. Then you've got, once it reaches its saturation temperature, so it went from 70 something degrees through the condenser. Once it reaches its saturation temperature, 63 degrees, once it reaches its saturation temperature, which in this case is 18 degrees, it starts to condense from a high pressure, high temperature vapor to a high pressure, high temperature liquid, and the pressure stroke temperature stay the same throughout. So this gauge line doesn't move. So if that was at 15 bar, in actual fact, if we look at 18 degrees, our head pressure then would be, so there's 10, 11, 12, so 10, 12, 14, 16, 18 and 20. So you can go across here and you can see that it's just above 5, 6, 7, 8, 9. It's about 9.1 bar, okay, pressure at 18 degrees. And remember, our normal operation was up at 15 bar, so there's something wrong here. But anyway, what we're saying is, how do I know that condensing temperature for an air-on temperature of 20 degrees and a condensing temperature of 18 degrees, how do I know that that's normal? And then, as I was also trying to say, is that how do I know that what my subcooling value is? Well, it's the difference between my condensing temperature as read from my high side gauge if I had a gauge fitted, or my condensing temperature as read from the middle of my condenser, and the temperature of the liquid as it exits the bottom of the condenser. In this case, there's 6 degrees. That's the subcooling value. And again, as I said to you last week, subcooling value should be a difference of between 4 and 7, and superheat value should be a difference of between 5 and 8. But getting back to the original question, which was, is the head pressure too low? Is my condensing temperature stroke pressure too low? Okay, so effectively how I answer that question is I say, okay, I've got in the middle of my coil, I use my thermometer in the middle of my coil, in my condensing zone, which is in the middle of my coil, in my condensing zone, I'm getting a reading of 18 degrees Celsius, and my air-on temperature is 20 degrees Celsius. So for an air-on temperature of 20 degrees Celsius, what should my condensing temperature be? And this is where we have to have the knowledge and know for a fact that for an air-cooled condenser, doesn't matter what size it is, doesn't matter how big it is, if it's an air-cooled condenser, manufacturers have designed them to operate with a delta T total of between 10 and 20 degrees of a difference. So what that means is that if I've got air coming on at 20 degrees, my condensing temperature needs to be minimum of 10 degrees higher or a maximum of 20 degrees higher than the air on temperature. So the lowest condensing temperature with an air on of 20 degrees, the lowest condensing temperature that I should have should be 30 degrees, and the highest condensing temperature that I should have should be 40 degrees. So when I put my gauge in the middle of my condenser, anything between 30 to 40 degrees is within the norm. You might even find that it's about 15, on average 15 degrees of a difference. So you might find that it'll be about 35 degrees Celsius condensing temperature. Then I know that that's the correct condensing temperature for the air temperature that's coming on. So for the ambient condition that the condenser is located in. So when the air temperature drops, so will condensing temperature. When the air temperature increases, so will condensing temperature. So this is why it's important to know that when we come to a system and we're going through the checks and balances, and we're determining, is the temperature that I'm getting at this component the normal temperature that I would expect, you need to benchmark it against the ambient conditions. In the case of the two heat exchangers, you need to benchmark it against the ambient conditions that those actual heat exchangers are located in. So in this particular case, This heat exchanger, which is a condenser, is located in an air on of 20 degrees. So the air coming onto the condenser is 20 degrees Celsius. The air coming off the condenser is going to be warmer because it's removing the heat from the refrigerant. But in order for the effective refrigeration to take place, so effective heat rejection to take place, or efficient condensing of the refrigerant to take place, the temperature of the refrigerant needs to be between 10 to 20 degrees higher than the air temperature coming on. So remember, in order for heat exchange to take place, there must be a temperature difference, and therefore when manufacturers are designing air cooled, and I keep putting an emphasis on the air cooled because water cooled it changes the rules. Water cooled water cooled condensers are 10% more efficient than air cooled condensers. Water cooled condensers, you can guarantee that the water is going to be constant even when you're using a water cooling tower, so you're kind of guaranteed a constant temperature. Air cooled, air temperatures fluctuate up and down. The warmer my air temperature, the higher my condensing pressure. The lower my air temperature, the lower my condensing pressure. But there will always be a difference of between 10 and 20 between whatever the temperature is of air on and the refrigerant circulating inside in the condenser or in the heat rejection heat exchanger. And again, I'm kind of going and talking about heat rejection heat exchangers because those of you in the split air conditioning business or in the heat pump business know that sometimes the outdoor unit acts as the evaporator and rejects heat inside into the space, and sometimes the outdoor unit acts as the condenser to reject heat to the outdoor space, allowing the indoor coil to remove the heat. So depending on whether you're on heating mode or cooling mode determines which heat exchanger is acting as which. But in refrigeration terms, you always have an evaporator which absorbs heat. You always have a condenser which rejects heat. And in this case, our condenser here has an air on temperature of 20 degrees and a condensing temperature of 18 degrees. So in our chart, is LP too low? Yes. And straight away then, without putting gauges on, I never put a gauge on the system, I can tell you with confidence the problem with this particular system is a lack of compressor capacity. In other words, what that means is that for some reason this compressor is not pumping properly. Now that could be from a cracked head gasket, it could be from a cracked or broken suction valve reed, it could be from a cracked or broken discharge valve reed. So there are numerous reasons why it's not pumping efficiently. It could be not because of the compressor itself. It could be because of an accessory component that has been fitted to the system is allowing discharge pressure enter into the crankcase side or the low side of the system. And that can commonly happen with, say, if you had an oil separator fitted onto the system. And the purpose of the oil separator is to separate oil from the refrigerant and return that oil back to the crankcase of the compressor. Now, if that float that allows the oil, once the oil level drops sufficiently enough, because too much oil is as bad as too little oil, but once the oil drops sufficiently enough, there's a management system, an oil management system, and it usually it consists of floats or sensors. But if for some reason the oil return line is left open constantly, because it's fitted to the discharge side of the compressor, you're getting discharge pressure forcing the oil back through the oil return line back into the crankcase of the compressor. Crankcases of compressors are usually low pressure, low temperature. In other words, they're on the low side of the system, and that would continue to allow discharge heading into the low side of the system, which would give you the reading of a lack of compressor capacity. In other words, head pressure decreases, back pressure increases, temperature goes up in the room, sign of lack of compressor capacity. So you might find it's a result of an accessory. So again, depending on the system, that requires further investigation. However, for your portfolio, you will go and answer the question. So basically, I just get rid of that out of our thing. We will answer the question. We go down. There's 9 faults, remember. And this one here, it's lack of compressor capacity, number 6. So we will go and we click on number 6. If I am right, it allows me then to go to number 2. If I'm wrong, it says total temps equals 1, but this number here would stay as 1. But this last completed task number 1. But the fact that this has gone to number 2 task means that I got the answer right. Now again, we come across another system here, and we find that our system here is not working, and the reason why it's not working is because we can see that the room temperature here, just looking at the cold room thermometer, is at 10 degrees. So this should be down at 2 degrees. This chill room should be down at 2 degrees, but we see that it's at 10 degrees. So therefore, we need to find out, well, why can't we get this room down to 2 degrees? What is the problem with this room that it is not getting down to 2 degrees? And again, I'm going to go and I'm going to use my thermometer. I'm not going to use my gauges. That's the last resort. I will only put my gauges on to determine what the problem is. Now,
You're breaking up for the last couple of minutes.
okay, where do I need to start? Am I still breaking up, or am I back?
You're grand here. Yeah, it's fine now. Yeah.
Okay. Where do I need to start? Where did I start to break up?
I don't know. I heard you perfect, so you can continue on.
Okay. So the other thing that I meant to say to you is, when we were at the lack of compressor capacity, what I also want to refer you to is back to the book. And in the book, it actually tells you, like, it explains about pumping down, for example, as well, which is thick. But everything we talk about is in the book as well, okay? And explains about problems with compressor. But this one, compressor efficiency test, okay? So it explains to you here, if you have a lack of compressor capacity, then you need to determine, well, what is the problem? Is it on the high side or the low side? So this here talks you through a compressor efficiency test, how to carry it out. But one of the things it tells you to do is it tells you to front seat the high side gauge valve or the high side service valve. So some of these would have a high side service valve, okay? Now, I would say to you, never ever front seat a discharge service valve on your compressor unless you can electrically isolate that compressor. You do not want the compressor, so it says here, look, functions of the compressor, suction, discharge, valve, efficiency. Oh yeah, front seat suction service valve. Okay. There is one there. I don't know where it says it there. Yeah, this one. Isolate electrically and front seat the discharge. Okay. So in other words, never front seat your discharge service valve unless you've isolated electrically. You do not want the compressor to start up with a fully front seated discharge valve, because that discharge pressure will have nowhere to go, because you'll be blocking it from getting into the discharge line, and that will cause problems. It'll break your compressor up. It will certainly break valve reeds or burst a gasket or build up to head pressure in it, okay? So what I would suggest is, when you do fault number one, which is the lack of compressor capacity, which is this one here, lack of compressor capacity, then you go to the book and you have a look at the compressor efficiency test, and that will explain how you check out that the compressor is pumping properly, okay? Now, getting back to this fault number two, again, we start at the very beginning. Because we are getting a room temperature of 10 degrees, the customer has called us. The room temperature should be 2 degrees. So first thing we ask ourselves is, have we got normal evaporating temperature stroke pressure? And again, we use our rule of thumb, 5 to 10 degrees of a difference. The other thing that I need to say to you at this point in time as well is that, and it's in our notes as well, that when it comes to a split air conditioning system for comfort cooling, for the air conditioning, the delta T total on the evaporator side is 15 to 20 degrees of a difference. So in other words, it's not unusual to have a room temperature or air on temperature of 18 degrees for comfort cooling, and an evaporating temperature of 5 degrees or even 7 degrees. So it can be anywhere between 15 to 20 degrees of a difference. That's how it works on a split system. On the high side of the split system, so on the side where the heat's being rejected out into the atmosphere, the outdoor coil during cooling mode, for example, it stays the same, 10 to 20 of a difference. It always stays the same. But when it comes to the cooling side, when you're trying to extract heat, the delta T total will be between 15 to 20 of a difference. Now on a commercial unit, which is what we're dealing with here, on a fridge unit, it's 5 to 10. So just they're just the two differentiations that I need to bring to your attention. Now, sticking with this particular job, we've got air coming onto our evaporator of 10 degrees, which matches up with our room temperature anyway. So what we need to do is we need to determine what is the evaporating temperature and work out the delta T. To work out the delta T total, evaporating temperature is 7 degrees. Now, is 7 degrees the normal temperature for air on of 10 degrees Celsius? No, because it's 3 degrees of a difference, isn't it? There's and it should be between 5 to 10 degrees of a difference, yeah? So, if anything, because it's 3 degrees of a difference, so if we were to take, it should be between 5 to 10, so minimum of 5 degrees lower, maximum of 10 degrees lower. In our case, it is 3 degrees lower. So when we look at this, we have to ask ourselves, is it too low, is it normal, or is it too high? Yeah, we see now we have to think carefully about this, okay? So, normal, let me put it a different way, right? Air on temperature, get me thermometer. Air on temperature of 10 degrees. Air on of 10 degrees, right? I am expecting an evaporating temperature of maximum evaporating temperature of 0 degrees, because if I take 10 from 10, that gives me 0, and a minimum evaporating temperature of 5 degrees, because if I take 5 from 10, that gives me 5. But if I say, if I took 6 from that, then I could have 4 degrees. If I took 7 from that, then I can have a 3 degree evaporating temperature. And if I take 8 from that, then I can have a 2 degree evaporating temperature. So that's, and 9 from that is a 1 degree. So anywhere between 0 to 5 degrees would be the evaporating temperature that I'm looking for. So air on, it should be 5 to 0 degrees lower. So if I have air on of 10 degrees, I need an evaporating temperature of either 5 degrees. If I take 6 off 10, then it's going to be 4 degrees. If I take 7 off 10, it's going to be an evaporating of 3 degrees. If I take 8 off 10, it's going to be evaporating temperature of 2 degrees. If I take 9 off 10, it's going to be evaporating temperature of 1 degree. And if I take 10 off 10, it's going to be evaporating temperature of 0 degrees. So my lowest evaporating temperature should be 0 degrees. My highest evaporating temperature should be 5 degrees. In this particular case, I have an evaporating temperature of 7 degrees, which means that the evaporating temperature is actually higher than what I would expect it to be. Does that make sense? So, is it too low? The answer is no, it's not too low, because it's actually higher. Too low would be anything lower than 0 degrees. So -1, -2, -3, -4 would be too low of an evaporating temperature. 6, 7, 8, 9, 10 degrees evaporating temperature is higher than what we would expect it to be. So anything from 6 up is higher. So 7 degrees evaporating temperature with an air on gives me a delta T total of 3. We need a minimum delta T total of 5 and a maximum of 10. In this case, we have a delta T total of 3. That delta T total of 3 means that my evaporating temperature is higher than I would expect it to be with the air on temperature of 10 degrees. So is LP too low? No. LP is not too low. If anything, it's too high. Goes back to, is HP too low? So let's go and have a look. Maybe I'm making an arse of this, but anyway, I get confused myself. So head pressure again, air on. Let's get our thermometer. Air on is 20 degrees. Condensing temperature, which is the middle of the condenser, is 45 degrees. So again, we have 15 degrees of a difference there. Is that what we said? 20. So, sorry, we've 25. It's 45, isn't it? 45 is what we have there. 20 on, is that what we have? Air on to condenser is 20. So that's 25 degrees of a difference, yeah? So again, what should we be getting? 15 to 20 of a difference is what we're looking for. So with air on of 20, we would add 20. The maximum condensing temperature we're looking for is 40. The minimum condensing temperature that we're looking for, even 10 to 20 is what I should have said. The minimum condensing temperature is 30 or anywhere in between. Okay, so it should be between 10 to 20 of a difference. Condensing temperature should be 10 to 20 degrees higher. In this particular case, it's 25 degrees higher. So then we go back to the chart. Is HP too low? The answer to that question is no. It's too high. Next question is subcooling okay? Subcooling is the difference between the condensing temperature, which in this case is 45 degrees, and the liquid temperature as it leaves the bottom of the condenser. So this little pipe here at the outlet of the condenser, that's 42 degrees. So is subcooling okay? That's 3 degrees of a difference. Subcooling should be between 4 and 7 degrees of difference. So subcooling is not okay, because normal or good subcooling should be anywhere between minimum of 4 degrees and anything above that. It works in between 4 and 7, but if you had 8, 9, 10, then you're saying your subcooling is excessive, so you would be saying subcooling is okay. If anything, it's excessive. But in this particular case, subcooling is lower than normal. So anything less than 4, it's 3 degrees lower than normal. So when we go to this chart, we can see, is subcooling okay? No. So then we have lack of condenser capacity. Okay? So now we've pinpointed it to the condenser. So the next thing we need to figure out is the delta T for the air quite large, and it's a yes or no. So let's have a look and we can see now. Delta T for the air means the difference between the air on, which is 20 degrees, and the air off should be between 5 and 10 degrees of a difference. So 5 to 10 degrees of a difference. So if I have air on of 20 degrees, I'm expecting an air off of 25 degrees minimum, and maximum of 30 degrees. So anywhere between 25 and 30. Usually it's in the middle. Usually it's about 6 or 7 degrees. So my air off, if it's coming on at 20, should be coming off at 26 or 27 degrees. In our particular case, it's coming off at 22.9, which is about 3 degrees of a difference. Well, it's 2.9 degrees of a difference. So if anything, that's too small of a temperature difference. It should be a minimum of 5 degrees of a temperature difference. Anything less is too small. So when we go back here and it says, is the delta T quite large? No. Then it's down to an exchanger fouled. Heat exchanger fouled up. So in other words, if we were doing this for real, you would probably notice that this is caked in dust, because this unit is actually sitting on the floor. So this is a bad place to put a unit, sitting on the floor, because as soon as the shopkeeper comes along and starts sweeping the floor, the dust is going to be sucked up into the fins and so on. So normally what we would do with this would be facing the other way. It would be in this extract grid here. It would actually be in, so the condenser would be outside drawing the air in, and then that air would be channeled back out a vent out the other side. So in other words, you'd be constantly, any air that's drawn across the condenser, because it's going to be hotter, would have to find somewhere, hot air rising, would have to find somewhere to exit. So it might exit a vent beside it, or a vent above it, or a vent on the back wall here, if that back wall was to outside space. Anyway, getting back. So then we go and we do our answer, and we say that it's lack of condenser capacity, and we say that it's a heat exchanger fouled, and we discovered that it's the heat exchanger fouled based on the fact that we were able to discover that because of the delta T being quite small across it. So we go down through our thing here, and it says, and we say lack of expansion valve capacity, lack of refrigerant, lack of expansion valve, lack of evaporator, lack of compressor, lack of condenser capacity, fouled condenser, lack of condenser capacity, lack of airflow. So we're going to go with number 8. See if we're right. Went to number 8. Now we must be right, because it's showing me number 3 here. If I got that wrong, it wouldn't show me number 3, it would stay on number 2, and it wouldn't allow me to go on any further. So you can do the rest yourself, as in there's 9 faults there, so we've only done 2 of them, and I'm trying to get you to use the I'm trying to get you to use the thermometer as a first resort and not to go near the gauge manifolds themselves. Only use the gauge manifolds as a last resort. The manifold would only go on for you to be able to carry out whatever repairs you need, or for you to be able to confirm the diagnosis that you make. Okay, so this was back to the portfolio, which is this one here. This is point number 10. It says complete the faults randomly, yeah? And then the next one says, when you have completed the faults, save and exit out of the test skills and enter into the Q&A section to complete the multiple choice sections. And then the last thing it asks you to repeat 1 to 11 as many times as possible, as these skills and knowledge will be required to complete the theory and the practical test. So in other words, complete everything. If you want to keep doing this, keep doing this, keep doing this, all the way back up as many times as possible. But really, the last two is where I would encourage you to keep going. And even, actually, yeah, all of it except for maybe instead of one, you're going to do, yeah, okay. So do the whole lot, the whole lot for as many times as possible till you build up a kind of cognitive knowledge on it. Now, the other thing that you'll see in the portfolio was asking you to go into this area here, which I'm going to show you now in a few minutes, and I kind of doing it. I'm doing it. I know we're going to run out of time now in a few minutes, but I'm doing it, and I know I've thrown a lot at you as well. And hopefully, when we tidy up the video, you'll be able to pick up on a lot of it. But I want you to come in here. This was number 11. Was asking you to go into this Q&A session, and again, what you'll find is that there are 37 questions in total, and we're going to start the test. And the test is going to ask you simple things like, what is the component called? So this component here, what do you think that's called? Is it a solenoid? Is it a compressor? Is it a condenser? Is it a receiver? And you click on any one of those, right? And make sure you're logged on when you click on those, because we'll record how many that you got right in the first time and see how you've improved and so on. So the idea being that if we keep, if you keep being able to answer these and go across these and be able to decide what they are, and even if you get it wrong, it'll still allow you to keep going on. It allows you to keep going through. So you can keep going through as many times as you like and call it whatever you want and do whatever you need. You may or may not get it right. You'll see I've randomly done it. There's one or two I think myself I might have got wrong. There's one or two I might have got right. But you'll go through those 36 and we'll save and exit and we'll go out of it. Now, and the reason why I'm saying I'm going a little bit by next week, so don't worry about it if you get frustrated and you can't answer those, or you do really bad, because the reason being is that what I need to do, or not that I need to, but what I'm going to do at one stage with you is I'm going to go through each one of these components. So for example, this is representing an oil separator, so I'm going to explain that to you so we'll know that. This represents a pressure switch, a dual pressure switch, high and low temperature pressure switch. This represents a crankcase pressure regulator, but it can also represent, if I was to exit out of those, it can also, or not exit, sorry, I want to go back into that. If I was to go back up, it can also represent the evaporator pressure regulator. So this here is representing an evaporator pressure regulator. That's evaporator pressure regulator, and the crankcase pressure regulator is closer to the suction side of the actual crankcase of the compressor. But the two I will explain. So this one, because of the nature of the way it is an actual crankcase pressure regulator, and I explained the function of that. Compressor. This is a room stat, solenoid valve, thermostatic expansion valve, filter dryer, two ball valves either side, so you can change the dryer, site class, and so on. But then this is showing you the electronic side of it, and then again you can see that in this particular case, this is a KVP, so that's representing an evaporator pressure regulator. This is a KVL, so that's representing a crankcase pressure regulator. And again, I'll explain how all of these work and how multiple things, and go through each one of the components, how they operate and so on, flow valves and all of that. Get you to, this is your class exercise that you got to do. You already have this sent to you. You're going to print that out and you're going to label that exercise. I'll explain the evaporator, so the different types of evaporators and how they work and what happens. So that'll be, you can go ahead yourselves. You'll find that in the book as well. So if you find that you want to learn how to do these, you'll find them in the book as well. So again, if I go back into this book here, and you need to go ahead, I'll explain them to you, but if you need to go ahead or jump ahead and do your own independent learning, you will find that as you go through along this system here, it explains each one and how so the vapor compression system, the components on the vapor compression system, and so on. Okay, so the contents are there. It tells you what you need to know. It tells you about the vapor compression system, which is this here, explains through you, explains about the different components and so on and so forth, the service valves, removing gauges, adding gauges, and all of that kind of stuff. So it's there for you to look through. But as I say, I'll be explaining all of these slides to you. This is like a thermostatic expansion valve where there's a distributor fitted and so on, and the effects that has on it and so on. So that's all for next week's class. This one here is an exercise, and we'll go through it next week as well, but you'll need to be able to have this printed out. Again, it was given to you as part of the handout that Shane sent separately along with the portfolio. So you'll be given this and you'll be asked to diagnose the problem. So what's the difference between what you see with normal operation and what you see with abnormal operation? And again, so I think I have the other way around. This says here normal operation, abnormal operation. So you go through it and you decide, but you give the rationale. So you give your thinking, you explain your thinking behind it, why you think that this abnormal is whatever you diagnose it to be. Condensers, then I'll explain condensers and the different types and so on. So they're all the different components and different compressors and so on. And then more detail of expansion valves and that kind of stuff. So and the suction accumulator, like I promised as well. So we get that for next week, and then the following week you're going to be with me back here in real time, and I'll be able to show you more practical examples of oil separators and suction accumulators and so on. And then we'll have a good question and answer session. We have the exam, the theory exam to do, and we also then have the practical demonstrations to do as well. So we'll have a good full packed day when you come back to me, and between this and then we can clarify anything. So have we any questions?
Yes, it's correct here. Sorry, but I didn't get any username and password that I can log in on the simulator.
Okay, you make that up yourself. So if I save and exit, what you do here is it'll when it comes to click to start. So when you download the new one, we go and we register. You write your username, you write your password, you verify your username, and make sure you give us your proper email so that if you forget your password, we'll be able to send you a new password instantly, or reset your password. So once you click register, you put in your username, you put in your password, you verify what password you made up, and you give us your email so that we can make sure then that if you ever have any problems or whatever. And once you've done all that, then you register. And once you've registered, then you log in with your username that you've given and your password that you've given, and you can even click remember me so it'll know you for the next time. And then when you log in, then we're able to keep going. Yeah, is that fair enough?
Okay, thanks.
Yep. Any other questions?
Just one quick one there. In one of the troubleshooting scenarios you had the air on temperature, I think was 20, and you had the bottom part of the condenser at 18 degrees. Can you actually get that where the lower part of the condenser has a lower temperature than the air that's cooling it? Yeah, that's because what was happening in that one, I think you found that it was there wasn't any air getting across, so basically because there wasn't sufficient airflow, there wasn't any heat exchange taking place. Let me think about that question. Actually, you have me on that one. Hang on a second. Can you get? Sorry. So that was that. I would have thought that
it would have got.
You could have got with something slightly bigger than ambient temperature, you know, at the bottom of the condenser.
Yeah.
That doesn't matter.
No, I hear what you're saying. Right. Okay. What happens here is you're going to have your 60, 70 degrees, so this is your de-superheating. And what happens here is you're going to have a slightly colder, because that's the condensing zone, and then what happens here is your subcooling zone, which is going to be colder again. So this is always, when you put your hand down along here, this will always be the coldest part. Now, I hear what you're saying in terms of it might be slightly wrong, or it is wrong, because if we had a fouled heat exchanger here, in fact, you'd find that your condensing temperature will be excessively high because you don't have sufficient air going across. So if you had 20 degrees going across and it was because of it all blocked up, in fact, what the opposite would happen, you wouldn't have an 18 degree condensing temperature here. The only time that you could find yourself with an 18 degree condensing temperature is as if the compressor itself wasn't pumping, or wasn't there wasn't any superheat built up inside in your discharge. So you're right, that's an actual bug in terms of the problem. The problem that we should have had, instead of 18 degrees, that should have been maybe 58 degrees or 48 degrees or something like that, rather than 18 degrees. So you're well spotted. Because basically the chart, what we're trying to do is we're trying to say, right, that lack of condenser capacity is down to higher than normal to higher than normal back pressure, higher than normal. It's actually normal to higher than normal head pressure. So in this particular case, we should have said so the head pressure was okay. So but 18 degrees would mean that the head pressure was too low. So this is when we got our lack of condenser capacity. So hang on now a second. That was fault 1 or fault 2?
I think it was the second one.
Yeah, there, 18 degrees. Sorry, this was compressor pumping. In this particular case, yes, you can have the 18 degree condensing temperature, because what's happening is that it's you've got your if we go back to our chart, you've got your low pressure, low temperature vapor, right, which is going to be slightly higher, equalizing with your high pressure, high temperature vapor. So that's why you're getting your 18 degrees. So in other words, the lack of compressor means that we're not getting superheated vapor. So this here will be high pressure, high temperature, superheated vapor coming into the condenser, but because for whatever reason there's no compression actually taking place in here, and so effectively what you're doing is you're getting low pressure, low temperature vapor coming in here, equalizing with whatever the high side is, the high pressure. So it's bringing down the high pressure and it's bringing up the low pressure. There's no compression, no heat of compression taking place. Therefore, the top of the condenser, this is where this is slightly wrong. The top of the condenser shouldn't really be this temperature here of 63 degrees. Top of the condenser is probably going to be, there's no superheat. It's going to be in and around the 18 degrees. So what you'll find is, where the fault is or where the confusion is, this shouldn't be as up at 60 degrees. If anything, it should be closer to the 18 degrees. It might be a little bit higher, but there wouldn't be the same amount of heat of compression that's taking place. So what the next one is showing you that your superheat or your superheated vapor is up at 70 degrees. So this 63 is showing that you're getting lower than normal, but in real terms it wouldn't even be as high as this. But it is definitely not at the temperature that you would normally expect it to be, which in the next scenario you will see it's up at 70 something, 71 or 72 degrees. But in actual fact, that 63 should be a lot lower. It should be a lot closer to the 18 degrees if it was a really lack of compressor capacity. But then also it also depends on whether it's because of a valve read, a gasket, or discharge pressure being exposed to the crankcase of the compressor.